We're starting off here with the 2019 Higher Level Question 12di part, which is the question on particle physics. Often this comes up as a solo question and you can get a full 56 marks for it, but in 2019 it was half of a question 12, so you get 28. So it starts off and asks about the two families of hadrons and requires you to name them, and the hadrons are baryons and mesons. Then they ask to distinguish between the two, so the definition of each basically. So baryons have masses greater than or equal to a proton, and mesons have masses between electrons and protons. So baryons B are bigger and mesons are mini, so they're masses between electrons and protons. So they're equal to or bigger than a proton, and then they're less. So then they ask about a pion produced in a reaction, and a pion must be produced as charge must be conserved in all reactions, so the pion being neutral will help conserve your charge. Then they move into a calculation question. So they tell you that the velocity of a proton is 0.9 times the speed of light. Then the mass of the proton is given as this from page 47 of the tables. The mass of the neutral pion, so that's pi zero charge, is equals 264 times the mass of the electron. So that's given on page 48, but that's a relative mass, so it's 264 times the mass of the electron. The mass of the electron is this much, which again is on page 47. So you have to multiply those two together, that gives you the mass of your neutral pion. Then the speed of light is given as this, again on page 47 of the tables. So one of the key ideas in this section is that you have a proton and they collide with energy, and that energy turns into these additional particles. So you have your two protons coming out and you have your neutral pion in this case. Momentum must also be conserved in all reactions, but this is actually, I went the wrong direction with it. So I tried to look at the momentum before and after, but that wasn't a useful thing that I needed to do. So what I have to do is skip over that, and I needed to find the change in mass. So the change in mass, I have a proton and a proton going in, so a proton and a proton coming out. So the only mass produced is the mass of that neutral pion. So because it's easy to calculate, they gave it in a difficult form. So that's 264 times the mass of the electron. Again, all of that is in your tables, and when you multiply that out, that gives you this full number here. And again, don't round off, just keep the number as it is. Key formula, E equals mc squared. So this is your generated mass, that is your speed of light as given in the tables. Remember to square it. So when you do that calculation, you get this amount of energy here in joules. So energy is equal to this. I wasn't asked for it in electron volts or mega electron volts, so I'll stick with it here. So it's 2.161395,664 by 10 to the minus 11 joules. Then they asked me to get the kinetic energy of the particle. So EK for kinetic is equal to half mv squared. That's your kinetic energy formula. So the mass energy before must equal the mass energy after. So the mass energy before, well, that came from the two colliding protons. So that's what the 2 is here for. Your two protons colliding, each with an energy of a half mv squared. So then 2, half, mass is the mass of the proton, and the velocity is the velocity of the proton. And again, that is given in the question in a kind of disguised form. They tell us the velocity of the proton is 0.9 times the speed of light. So we can calculate that up here. It is the mass of the proton by the velocity, 0.9 times the speed of light squared. And when you throw all of that in, that gives you this value times this value. So that's the mass of your proton, and that's the velocity of the proton. I couldn't really fit them on both lines. 2 by a half gives 1, so that's where that disappears to. So this is my mass energy before. It's 2.12176547113 by 10 to the minus 10 joules. So that's the energy going in. We found out that this is the energy that's converted into the pion. So the kinetic energy of the pion then is the rest. So we have this figure here, which is the total energy going in. So we copy that down here. We take this amount of energy, which has been turned into mass. So that leaves this much left over. So that leftover energy is the kinetic energy. So you take this amount to be turned into mass, and then this rest will give it its kinetic energy, basically its velocity. Again, in an easier example, you have 100% energy before. If it takes 10% of that energy to turn into mass, what's the percentage left? That percentage left will be kinetic energy, and in that basic example, it's 90%. So it gets tricky when you get these long figures, but if you just take it at that basic kind of idea, it makes your life easier. So that's the last part of the calculations. Then they ask us how protons are maintained in circular motion in Large Hadron Colliders. So they're kept in their paths using magnetic fields. And then a few advantages of circular accelerators over linear accelerators are, first off, greater speeds can be achieved. Similar is greater energy can be created, so the greater speeds can give you greater energy, and that calculation kind of shows why. When you got the protons up to 0.9 times the speed of light, which is the fastest thing in the universe, you can then get pions and things created, and you have large energies left than as kinetic energies. More energies means you can have more particles. Another advantage of the circular accelerator is particles can travel along longer paths, so you get them going round and round. So those three are kind of the same. Get them going round and round, so they go faster and faster, and you get more and more energy. Another kind of different one then is circular accelerators are more compact and require overall less space to generate large speeds. If you had a linear accelerator, you're going to need a very long stretch to get up those speeds, whereas in circular accelerators you can bring them round and round. So we're going to keep going through exam paper questions. That's the 2019, so the latest one that was asked. You can see it's kind of consistent in what they ask, so that question leads into these follow-up theory ones. You do need to know a bit of everything, and I'm going to work through some other exam years as well, and then you'll maybe get a full range of what they can ask. It's a relatively short chapter, so there's only so much they can ask, and then try and spin it in different ways. But there are your advantages of circular accelerators, an equation, mass energy and kinetic energy, and then some background on baryons, mesons, the two types of hadrons.